Alright, today we are talking about slope and parallel lines. There is actually a theorem about the relationship between slope and parallel lines. You probably learned it in Algebra 1 about how parallel lines have the same slope. But there is actually a theorem that goes with that, and that's the theorem we're going to be using today. We are just going to call it slope criteria for parallel lines. Which is like what I said, where you have learned in the past that parallel lines have the same slope. The theorem says that two non-vertical lines are parallel if and only if the two lines have the same slope, or they have the same slope. This is especially important for proving that certain figures are either parallelograms or rectangles. We're going to talk about trapezoids. All this matters with the definition of the quadrilateral as well as the relationships between the segments and the parallel sides. So we're going to do these first two examples. The first one says, number 4 says that show that JKLM is a trapezoid. So we have JKLM over here. A trapezoid is a quadrilateral with at least one pair of opposite sides parallel. So that's what you need to remember. You have to know the definition of a trapezoid. If it is at least one pair of opposite sides parallel, we do have the picture so we can look and see what's going on. These two appear to be parallel, so we're going to try JK and LM first to see if they're parallel. Using our criteria of slope, we're going to find the slope of each segment first. So let's find the slope of JK. Now you should know how to find slope from Algebra 1. If you have forgotten how to find slope, it is rise over run. From J to K, to get from J to K, we rise or go down 2, and we run, go over 1, 2, 3, 4, 5, 6. So the slope is negative 2 over 6, which reduces to negative 1/3. We then need to find the slope of LM, since we think that that's the one it is parallel to. I'm going to go ahead and find the slope of LM, or ML, they're the same. Again, by counting our slopes. So to get from M to L, we're going to go down 1 and over 3, which is negative 1/3. Since these two slopes are congruent, or are the same, that means JK is in fact parallel to ML. Since the slopes of JK and ML are parallel, are the same, that means that segments JK and LM are parallel. Then, since they are in fact parallel by the definition of a trapezoid, JKLM is in fact a trapezoid. These are technically proofs, even though it says show. This is something called a coordinate plane proof, which I like better because you get to use actual numbers. Alright, next we're going to go and talk about how ABCD is a parallelogram. The definition of a parallelogram is that both sets of opposite sides are congruent, which means we're going to have to do both. We are going to therefore look at the opposite sets, and we're going to find their slopes. So first we need to look at the slope of AB. And the slope of AB, rise over run, I'm going from A to B. A went up 1, 2, 3, 4, 5, 6, and ran 1, 2, 3, 4. So 6/4, which reduces to 3/2. And likewise, we're going to find CD or DC. And it goes up 1, 2, 3, 4, 5, 6 over 1, 2, 3, 4. So it is also 6/4, which reduces to 3/2. So AB is in fact parallel to DC. That's just half of it. We've got half of the definition there. We've got one set of opposite sides. I'm going to mark them over here on my picture. We now need to do the other set, BC and AD. Notice the instructions say show. It does not say prove or disprove, which means it should be true. So the slope of BC, from B to C, I'm going to go down 2 and over 1. So -2 over 1, which is the same as -2. Likewise, from A to D, I go down 2 over 1. So it is also -2 over 1, which is just -2. So we have another set of parallel sides. Since both pairs of sides are in fact parallel, I'm going to mark it, we know that ABCD is a parallelogram. So that's how I'm going to write the answer. Since, there's that up so you can see the answer. Since both pairs of opposite sides are parallel, ABCD is a parallelogram. If you were absent, this page was on page 498 of your textbook. That's where we tore that out of. We're also going to do a couple more examples, and again, if you're absent, you're tearing those out of page 500. Okay, to finish these slope and parallel line notes, we are now working on page 500. If you were absent and you tear that page out of your book to finish these, we are supposed to find the coordinates of the missing vertex in each parallelogram, which means we're going to have some figure that has two opposite sides parallel. They already give us the first 3 coordinates, and we're going to have to find one of the missing ones. So first, we're going to go ahead and graph these. K is at 0, 1. M is at 1, -3. Then we're going to take our straight edge and connect them, which will help us see exactly what we may or may not. We are missing L. That's what we have to find. So we need to know where is L located. So to find where L is located, we are going to count slope. Now it really does not matter where I count. I can count the segment JK, or I can count the segment JM. Just know that if I count from J to K, I would have to go from the bottom coordinate M up. If I counted from J to M, I would have to go with the leftmost point and over. So I'm going to go ahead and count J to K. So from J to K, I'm going to rise 1, 2, 3, and I'm going to run 3. So I'm going to go down to M, because J was the bottom point. I'm going to use a bottom point M then. So 1, 2, 3, 1, 2, 3. L should be there. I'm going to connect, which will help me count and make sure I've done the right thing, that this really is a parallelogram now. Now I already created the rise 3, run 3 for this side, so this side's slope is in fact 3 over 3. But we're going to count the rest of them. So from J to M is down 1 over 1, 2, 3, 4. So the slope is -1/4. So let's make sure KL is also negative 1/4. So down 1 over 1, 2, 3, 4. Since both opposite sides are in fact parallel, L is located at 4, 0. We're going to do number 8 as well now, which is the same process. I've got D, E, F, G. I've got E, F, and G, so I'm missing D. So to do that, I'm going to graph negative 2, 2, which is E. F is 4, 1. G is 3, negative 2. And again, I'm going to go ahead and connect them. I'm missing D. So just like this one over here, I can start and count from E to F. If I do that, I would then have to go, because E to F should be the same as wherever D is to G, which means it's going to be a little more difficult. Or I can count G to F. Again, I would have to start from wherever D is supposed to be and go to E, which means we're going to have to kind of do the opposite here. I'm going to go ahead and count E to F. So that's down 1 over 1, 2, 3, 4, 5, 6. So it's negative 1/6. However, that was down from down and then over, and that is from left to right. Well, my point D should be over here on the left somewhere. So I'm actually going to have to do the opposite of that, which is go up 1 and left 6. 1, 2, 3, 4, 5, 6. So D should be there. We're going to check just like we did for number 7 as soon as we use our straight edge to complete it. Okay, let's count to make sure we did the 1/6 correct. Down 1 over 1, 2, 3, 4, 5, 6. That is negative 1/6. Okay, now DE is up 1, 2, 3 over 1, which is just 3. And GF is 1, 2, 3 over 1, which is also 3. Therefore, we did do that one correctly. So we do have a parallelogram.